All right, in this video we're going to consider the molar mass as an average of all the naturally occurring isotopes for any element. That average molar mass is what appears in the periodic table. Why do we have to consider this as an average? Well, most elements have more than one isotope. And remember that the difference amongst isotopes is different numbers of neutrons in the nucleus, which means that each isotope is going to have a slightly different mass. Now, fortunately, each sample of an element that I encounter on Earth will have exactly the same composition or ratio of those isotopes. So if I take an average, then I can use that to represent the actual molar mass of any sample of that element that I would encounter on Earth. So first of all, let's consider the difference between a weighted average and a simple average. To do that, let's look at this example. Let's suppose that 3 chemistry instructors get together. They decide at the end of the semester they're going to give their students a standardized exam. What they want to find out afterwards is what is the average overall for all the chemistry students at that school. And we find that Professor Potter's students had an average score on this exam of 78.8%. Professor Weasley's students had a 72.6%. Professor Granger's students a 76.5%. Now it seems like we ought to take a simple average of those three, 78.8 plus 72.6 plus 76.5 over 3. If we do that, however, we're ignoring that there are different numbers of students in each class. Turns out that Professor Potter has 44 students in his 2 sections. Professor Weasley has 34 students in his 2 sections, and Professor Granger's a part-timer, so she only has 22 students. Not really sure why Professor Weasley has only 34 students. Maybe it's because his ratemyprofessor.com score was a little bit lower, so that could be why. Anyway, when I take the total, I find out that there's 100 total students, and you can see that I ought to be weighting Professor Potter's average a little bit higher than Weasley's and a little bit higher than Granger's. So let's figure out how we would do that. The weighted average is going to be 44 times Potter's 78.8, 34 times Weasley's 72.6, plus 22 over Granger's 76.5. Now what am I going to divide by? I don't divide by 3 because I actually want to divide by the total number of students. So I'll divide by 100. There's my weighted average. So let's go a step further and let's distribute that 100 in the denominator into each one of the terms as a fraction. So when I do that, what I get is my weighted average equals 0.44, or 44 over 100, times the 78.8, 34 over 100 times the 72.6, plus 2200 over 76.5. I go a step further yet to evaluate each one of those fractions as a decimal. When I do that, what I find is the weighted average is 0.44 times 78.8, 0.34 times 72.6, 0.22 times 76.5. This would be what we would call a weighted average, and it must be true that when I take all the weighting factors, they have to add up to 1. Turns out that they do. 0.44 plus 0.34 plus 0.22 equals 1. And if that's true, then my weighted average will be accurate. So here's my correct formula for the weighted average of all the exam scores. So let's go ahead and finish the evaluation. I find out that when I do the math, I get 76.186. Now, there's a few more digits of precision there than I can really keep because my exam scores are only precise to tenths place. So let's consider how I would look at the rounding. Well, if I look at each one of the exam scores, I am 3 significant figures. And if I look at each one of my numbers of students, I have to realize that each one of those numbers of students represents a whole number. Now, I can't have a fraction of a student, so those would be exact, so that my fractions out front are not going to contribute to significant figures. So I'll end up with only 3 significant figures, and my final value for the average is going to be this 76.2%. Let's take that same idea of a weighted average to this problem, where I need to calculate the molar mass for silicon, which has the following stable isotopes. There's 3 of them, silicon 28, silicon 29, and silicon 30, each differing by a different number of neutrons. And I can see the mass in grams per mole of each of those isotopes, as well as their percent abundance. Now, to get the weighted average, what I need actually is not the percent abundance, but since all of my numbers have to come to 1, I want to move that decimal place a couple of units to the left to get the fractional abundance. So 0.922297, 0.046832, and 0.030872. My weighted average then will be to take the isotope mass of each one of those multiplied by its fractional abundance and add all that together. So weighted average will be the 0.9229297 times the 27.9769 for silicon 28, the 0.046832 times 28.9765 for silicon 29, the 0.030872 times 29.9738 for silicon 30. When I add all of those together on my calculator, what I get is 28.0853895. Now again, I kept all the digits that my calculator will give me, and I need to come back and round that answer. So how would I do that? Well, what's limiting my digits of precision? I find out that my limitation is in these two relative abundances right here. I have 5 sig figs for this one, 5 sig figs for this one. Now this one is 6 significant figures. All of these guys are 6 sig figs. So my limitation will be the 5 significant figures from the fractional abundance of silicon 29 and silicon 30. So rounding my final answer, I get 28.085 grams per mole. And if you look at the periodic table, you find out that that's exactly right. Let's do one last problem where I can use my knowledge of weighted averages to calculate fractional abundance of the 2 isotopes of chlorine 35 and chlorine 37. So chlorine has these 2 stable isotopes with their masses given. I want to calculate the fractional abundance given that the average molar mass of chlorine from the periodic table is 35.453 grams per mole. Now, I will use my knowledge of weighted averages knowing that the fractional abundances of my 2 isotopes have to add up to 1. So if I assign X as the fractional abundance of chlorine 35, the fractional abundance of chlorine 37 must simply be 1 minus X. So now I can calculate my weighted average. I'll take the isotope mass of chlorine 35 times its abundance, add to it the isotope mass of chlorine 37 times its abundance, and that will equal my weighted average. Now in this case, I already know the weighted average. The weighted average is 35.453. So that will equal X times 34.968853 from chlorine 35, plus 1 minus X times 36.965903 from chlorine 37. All that remains then is to calculate through algebra my value of X. Now, there's a few steps that will be required, but all fairly simple. First thing we're going to do is to rewrite the right-hand side and also distribute this 1 minus X times its multiplier. The left side of the equation will remain the same. 35.453 will equal 34.968853X. When I do the distribution, I get 36.965903 minus 36.965903X. The next thing will be to collect my values of X. I'm going to go out here to the right and do that. 34.968853X minus 36.965903X. When I do that math, I get minus 1.997050X. I'm going to keep that last trailing zero for now, since I don't want to do any rounding at an intermediate step. So then let's take this value and substitute it in for our collective values of x on the right side. The left side remains the same, 35.453 equals minus 1.997050x plus what's left from my right-hand side, 36.965903. Next, I'm going to subtract the 36.965903 from both sides. That makes that go away from the right-hand side, but now I need to change the left-hand side. So let's go out here to the left and do that calculation. 35.453 minus 36.965903. When I do that math, I get minus 1.512903, and I'll again keep all those digits of precision for now. Now I can substitute this on the left-hand side of the equation, and I get minus 1.512903 equals minus 1.997050x. The last thing to do is to divide both sides by the minus 1.997050. When I do that, I get x equals 0.75756891. And again, I've kept all the digits of my precision that my calculator gave me. But now it's time to round my final answer to reflect the digits of precision that truly exist in my data. I have three components to my data. I have the isotope mass here, and each of those two is precise to 8 sig figs. But then I have this, my weighted average, which has only 5 sig figs. So that's going to limit my precision in x to a total of 5 sig figs. The leading zero doesn't count, so rounding to 5 sig figs, I get 0.75757. Taking 1 minus x, I get 0.24243. So let's collect those two, go back up to our table for our fractional abundances. Find the fractional abundance of chlorine 35 is 0.75757. The fractional abundance of chlorine 37 is 0.24243.